Hello everybody, how are you today? In this session, we're going to talk about a very simple um, covariance relationship. So, so if you have a covariance, okay, so let's say you have a covariance between two series. Okay, so you have XS and ZT series. Okay, so this value will equate to 0 if the lags between S and T, actually S is lag of T, in other words. Okay, so what is actually the uh, XX, and so if you're talking about MA1 model, okay, how to relate this to MA1 model? So you have a XT with the ZT plus theta 1, ZT minus 1. Okay, if you have a series of lag of S, then basically you're going to have something similar to this S minus 1. Okay, S minus 1. So if you have a covariance between the SS and ZT series, so what is, of course, the ZT, in other words, will be following a white noise with a mean and constant variance. Okay, similar to this, your ZS is also a white noise with a random, uh, normally distributed value with mean zero variance sigma squared. So in this case, if you substitute the covariance of XS, which is ZS plus theta 1 S minus 1 with ZT, then we can say that the multiplication of the covariance ZS and ZT plus the linear relationship. So you have a theta 1 covariance of ZS minus 1, then you have a ZT. Okay, so obviously if ZT or ZS is normally distributed, or which is following a white noise, most probably the relationship between ZS and ZT will be 0. Or in other words, ZS and ZT, covariance of ZS, ZT will not be 0 if the S equivalent to T, like in other words. Okay, so for S less than T, okay, less S than T, that means the S is, if T is actually today, then S will be yesterday, like in other words. Okay? If T is yesterday, then S will be 2 days uh, after. Okay, so in this case, S is lag of T, most probably the covariance between these two random process will be 0. Okay, will be 0. So similarly, the ZS minus 1 and ZT, so this is even behind, another step behind or lag behind. So these two, the covariance will be 0 as well. So in other words, the covariance of XS and ZT will be 0 if S is less than T. Okay, so this is a particular case. So what happens if we proceed to MA2? Okay, MA2, we know that the XT is equivalent to theta 1 ZT minus 1. We have theta 2 ZT minus 2 plus ZT. Okay, similarly, you have XS theta 1 ZS minus 1 theta 2 ZS minus 2 plus ZS. So if you like to find a covariance between these two, XS and XT, then this is equivalent to, so most probably you just need to find out this using the similar way, we should be able to find out S minus 1 theta 2 zs minus 2 plus zs and the xt. Okay? Xt. Oh, sorry. So this should be the zt. This should be the zt. So we want to check the relationship between the zt here. Right? xs and zt. Right? That is the, because this result is quite important for us to derive the autocorrelation function afterwards. Okay, so this is the zt. So in this way, you have three pairs of linear relationship. Covariance of zs minus 1. Another one is theta 2. Covariance of zs minus 2 and zt. So lastly is the zs and zt. Zs and zt. Okay, so this will be the three linear components. So if s is less than t, that's when this and this will not have same z legs. Okay, so if they are not the same, so all the terms most of them will become 0 plus 0 plus 0. So overall is 0 if s is behind t. Okay? So this result is quite useful for us to derive the autocorrelation function afterwards. Okay, so this is MA2 models. This is MA2. This is MA1. So you just extend the XS and ZT. Basically, this XS and ZT as well. Okay. Okay. So this will be quite useful for us to determine the SCF afterwards. Okay. So in short, our purpose is to find out, I mean, to use this result afterwards. Okay? This result without any proving afterwards. Okay, guys. Thank you very much. See you guys out.